How goes it?
Maximum likelihood that.
Well, after I talk a little bit more about the discrete approximations to discrete distributions, and then we'll talk about maximum likelihood estimators. How did the video go? Good. Well, good. You didn't watch it? Oh, okay. All right. Well, let's talk a little bit more about the approximations to discrete distributions using the normal. We just started that on Friday, so I wanted to do some examples. I also wanted to play around a little bit more with Excel and show you a few more commands with that, and then get into maximum likelihood estimator stuff. All right, so this is 5.7-6 in your book, obviously, since that's what it says. All right. So I'm not as worried about the setup of the problem, just the numbers that we need. So it tells you that we've got 70% of cases that cause pneumonia. We've got a random sample of 84 adults, and we want to figure out the probability that X is, if X is counting the number that of people who had pneumonia, we want to calculate the probability that X is less than or equal to 52. So the first thing we need to do is figure out what kind of distribution we're even talking about before it says use the normal approximate. Yes?
Are you recording this?
Hmm?
Okay. It doesn't have like the little line.
It's because I did the full screen. When I do the full screen, the lines go away. Thank you for asking, though, because I certainly have forgotten. All right, so the first thing we need to do is figure out what kind of distribution are we even talking about. Before we did, obviously they want us to use the normal to approximate it. But what kind of distribution are we talking about to start with?
Binomial.
And how do you know?
It's the dad. It has to be pneumonia or they don't.
Okay, they either have pneumonia or they don't, right? And so 70% of the cases of pneumonia are caused by that particular bacteria, but we know that each individual adult has a 70% chance of having the pneumonia being caused by that particular bacterium, right? And then we've got 84 adults that were randomly sampled. So we've got independent, identical trials, right? Where you've got success or failure. So this is definitely a binomial distribution. What's the n in this case? 84, and p is 0.7. So that's our original distribution. What the problem's asking us to do is to use the normal distribution to approximate the x being less than or equal to 52. Now, before the advent of things like Excel or SPSS or R or those kinds of things, before the advent of that, either you needed to go have binomial tables that were rather robust, cumulative binomial tables that were rather robust, or you'd be sitting and trying to add up 53 things, right? Because for it to be less than or equal to 52, it could be 0, 1, 2, all the way up to 52. Right? Which would take a while. Okay? So this is one of the reasons why we might want to approximate this using normal distribution versus actually trying to compute it exactly. Now, of course, I'll show you in Excel how I can do this exactly. It doesn't take any time at all, except for typing the command. It's a lot of time. Okay? But let's talk about why this is going to work nicely for us for an approximation. So to that end, I created a little thing in GeoGebra. Okay, minimize them, that's fine. So let's see here. Where is it? There it is. It opened. Or try again. All right, so the idea behind using the normal distribution to approximate the binomial is a central limit theorem idea. Why are you not opening? Seriously, every time it's just open. Okay. try it this way. Not sure why it's not opening. Is a central limit theorem idea. Remember, when we think about a binomial distribution, we can think of that as a sum of independent Bernoulli trials, right? And when we do a sum of independent random variables that are identically distributed, the distribution of the sum is approximately normal if your n is large enough, right? And you know how to compute the mean, and you know how to compute the variance in those cases, right? It's n times the mean and n times the variance, okay? But just to see what's going on, because we have to actually make an adjustment here when we do the approximations, and to see why, hopefully this demonstration will do it if I can actually open it. I don't know why it wasn't opening. There we go. Cool. Okay. So let's just look at this. So what I made was here is just I put a binomial distribution and then put a normal distribution over the top of it that had a mean and variance equal to the binomial. So one of the things that you can see here is that when our n is relatively small, I've got it down at 14 right now, I've got bigger chunks of this rectangle here on the outside that aren't being matched by missing things inside, right? So I don't have that great of an approximation here, right? Okay. However, if I move my n to be bigger, notice that things even out a bit, right? And I get a better approximation for what's going on. Okay? So, when I get this is central limit theorem idea, if I keep pulling this over a little bit more, it gets a little bit better. I didn't make it very big because I didn't want to have to make the screen large. But the idea here is that if your n and your p behave well enough, you get decent approximations. You can see why I want to make sure that n times p or the n times 1 minus p give you that greater than 5 idea. If I have p very, very small, notice I've got this skewed idea. I've got pieces that miss quite a bit, right? This whole rectangle piece here is outside. I've got pieces here that I'm missing on the inside or gaining on the inside. This isn't a very good approximation. And the same thing happens if I flip. Move my end to the other side here. If I flip to the 1 minus p being small, I get the same issues, right? I don't get a good approximation to the binomial. Okay. So, from the picture, hopefully you can see why we need to make sure that n times p and that n times 1 minus p idea needs to be at least big enough to make making up the difference of what you miss and what you gain by the rectangles being either not on the outside or not on the inside kind of idea. Okay. So to that end here, but let's talk about how we're going to do this approximation. Okay. So if we look at the approximation, especially here on the tails, notice it looks like the normal distribution is kind of going right through the middle of the rectangular boxes, right? And we got this piece here that's hanging out, but it's made up by that piece there. We got this piece here that's made out or hanging out, but this piece here is making it up on the inside. But notice it's going right through the middle, correct? So if we want to get a good approximation here when we're doing the normal distribution, we do what's referred to as integer correction or continuity correction. And we do this by looking at the halfway point in between to make sure that we catch what we need. So, for example, what I mean with this is, going back to the original problem, we want x is less than or equal to 52, right? So I want to make sure that when I do my normal approximation, I catch 52 with a continuity correction or an integer correction. So when we do this for the normal distribution, I'm going to start at 52.5 and go down. Okay, so we're going to go halfway in the interval and make sure I catch 52. Okay, because if I start right at that 52, we see that we've got an under piece that we missed. If I go back over to the other picture here. Say over here, if I would start right at 52, notice I'm gaining something that I should, either gaining something that I shouldn't or losing something that I should. right? So I want to make sure that I start at a halfway point to try to make up where this is sticking out and where that's missing. See the idea what we mean by that by trying to adjust for that half. All right. So going back over here to the distribution, here's the binomial. The binomial again is made up of n independent Bernoulli trials that are, you can think of as being added together, right? So in this case, there's 84 Bernoulli trials, either 0 or 1, that have been added together, right? The central limit theorem says that if I take n big enough, then the sum is approximately normally distributed with a mean that's n times the mean of each and a variance that's n times the variance of each, right? Well, for an individual Bernoulli trial, the mean is p, and the variance is p times 1 minus p. So if I do n times, I get n times p and n times p times 1 minus p, which is exactly what you get for the mean and variance of this, right? So we're going to use, for this particular example, we're going to use mu is equal to 84 times 0.7, and sigma squared is equal to 84 times 0.7 times 0.3. It's, remember the variance is n times p times 1 minus p, okay? So we're going to use that mean, that variance, and so then we'll let y, be normal on, what is that, 84 times, what is it? 58.8, and then the variance is?
17.6.
So our y is going to be a normal distribution on mean 58.8, variance 17.64. Then the probability that x is less than or equal to 52 will be approximately equal to the probability that y is less than or equal to 52.5. The thing that you have to worry about with the integer correction or the continuity correction, same concept. Okay. The thing we have to worry about with what we use for the decimal here is whether or not we want to catch this boundary point or not. So if this would have said just strictly less than 52 and we didn't want to include the 52, we would have used 51.5 instead of 52.5.
That's only if we did it.
If the equal sign weren't there.
Okay.
Yeah. So whether or not you go right or left is dependent upon whether or not you want to catch the boundary point or not. Okay. In this case, we want to catch 52, so we use 52 and a half. Does that make sense? Okay. And then we do this just like we did with all the normal problems, right? We subtract the mean and divide by the standard deviation. So this will be, this is set up exactly like a standard normal, well, not standard normal, but just like your table will be because it's less than or equal to, right? So this will be phi of what? 52.5 minus 58.8 divided by the square root of 17.64.
Negative 1.5.
Exactly?
Yep.
Okay. So it's set up as a less than or equal to already, so it's set up as CDF, right? Okay, so I can just plug it directly into the phi, but I still need to standardize it. So I need to subtract off the mean, divide by the standard deviation, be negative 1.5. This we can look up in the table, right? What do you get if you look that up in the table? Well, it'd be, what's that? Oh, well, let's see if I have a table. I might have it. Oh, I deleted it. I deleted the old notebooks. I'm so awful. Yep, yeah, we did. I'll have to put it back in there again. I forgot I was cleaning it out and I deleted the old notebooks. Sorry. Oopsie. You look at 1.5 and subtract it from 1. Yeah.
0.4332. Subtract it from 1. Like 1 minus whatever it is.
That must be 9332.
Oh wait, this is going the other way.
Yeah.
Just kidding. This is not the left scale table. So
That's like the, oh, that's the middle.
yeah, it's in the middle. We can do the math.
I guess that should be 9332. Yeah. So this should be 1 minus 0.9332.
Yeah, I think that's middle.
Where'd you get a middle table?
Regression.
Oh, sorry.
Sorry.
It's not your fault. Unless it is your fault.
It is my fault. I totally did it.
I said your fault.
I'll take blame. I got broad shoulders. It's fine. All right. Does this idea make sense? What we did?
Every time you have a problem like this, you're going to adjust it to half.
Yeah, adjust with a half. Yep. Because we're trying to approximate a discrete distribution with a continuous one. So if you think about that histogram bars, we're always going to have some that we miss and some that we gain. So we're trying to make up for that. Now again, with the advent of computing devices like Excel or even your calculators, you've got cumulative binomial, cumulative Poisson, those kind of things already built in. So in Excel, I can do a cumulative binomial. So if I start typing in the binomial, notice there's a binom.dist. Right. Binom. All right, so then it asks for, the syntax has number that you're looking for, so this is number of successes. The next part is number of trials. Next part is probability of success, and the last part is whether or not you're doing cumulative. So it's got 4 pieces to it. So we were looking for 52 successes, right? Out of 84 trials, where the probability of success is 0.7, and it is cumulative. So there's, again, 4 pieces to that. It's number of successes, number of trials, probability of success, whether or not it's cumulative. And in that case, we got 0.06898, which is close to what we got, wasn't it? It was 668? 0.668? 0668. I said it wrong the first time. We could do the normal distribution on this as well. So the x value we were looking for was 52. This was the continuity correction, right? The x value we were looking for was 52.5. The mean was 58.8. The standard deviation is the square root of the 17 point, I forgot the number. 64, thank you. And then again, true for the cumulative. This is literally computing the phi of negative 1.5. Since I already did the negative 1.5, there's also the standard normal on here too that we could have used. But this would have saved us having to do the standardizing if we would have just typed it in right away. So you can see that they're close.
Why is it off?
Because we're approximating with the null.
Okay.
So it should be off.
Okay.
That's it.
So how much should we add or subtract? You got a 0.5.
It's always the half. The rule of thumb is to use the half. And that's why we're off a little bit. I mean, there's, by intermediate value theorem ideas, there should be a spot exactly that gives you exactly what you need. But what if we do that? Good luck finding it every time. So there should be a spot because you have over and under estimates Actually, I think I really mean mean value theorem for integrals, but either way, there's a spot where you could use, but the chances that you're going to find it are pretty small. Here's what it is. This okay? We can do the same idea with Poisson, by the way. Let's see if we can get an example of that. Put my samples back up again here. Is this one Poisson? Hey, look at that. That one was Poisson. You think I prepared for class or something? What's that about? All right. So let's think for a second about why we can use the normal distribution to approximate a Poisson. Again, the idea behind this is like we did in the previous example. A binomial you can think of as a sum of independent Bernoullis, and then apply the central limit theorem, right? You can think of the same idea for a Poisson distribution. You can think of a Poisson distribution as a sum of individual Poissons, right? Because we know if we chop it up into smaller time intervals and then add them together, we know that the sum of independent Poissons is Poisson, right? So, for example, this is counting per second. Maybe you count per millisecond instead of per second, and then add up those 1,000 things. That's still a Poisson distribution. Central limit theorem says that we should be able to approximate the sum using a normal, right? It's the same concept, right? Yeah. Okay. So it's the same idea here. That's how we're able to do this. Now, this is what I was just mentioning a second ago of whether or not you want to include something in your calculations for the approximation here. So in this case, what would we use? What would we use for the mean and the variance for the normal distribution? Okay, so I should use 49 for both of them, right? And why is that? Yeah, the mean and the variance for the Poisson is lambda, correct? Yep. All right. So then, the probability that our 45 is less than x is less than 60 will be approximately the probability that your y is in between two values. But like I mentioned again, I have to be careful of whether or not I want to include my boundaries. Do I want to include the 60? No. So where should I have the top end of this be? 59.5. Do I want to include the 45? No. So where should I have the bottom end?
45.5.
Good, 45.5. I want to miss it, right? Because there's no equals here. That's why. Okay, yep. So I said we have to be a little bit careful with the less than or the less than or equal to. For continuous, it doesn't matter, right? And so much of what we did at the end of last semester was continuous distributions. So we didn't worry about whether or not there was an equal to sign there or not. Since it's continuous, we know that the probability of actually being equal to that number was 0. Is that true for discrete distribution? No. That's why we have to be cognizant of where we're ending these intervals. So then, this one we can rewrite as phi of 59.5 minus 49 over square root of 49. That would be taking care of the upper end point, right? We're subtracting the mean and dividing by the standard deviation. Right? Now that catches everything below 59.5, so what do I need to subtract off? Good. Yeah, I got to subtract off the left tail, right? We agree? See? Okay. And now I might as well do this in Excel since we've already seen how to do that. All right, so go over to Excel again. So, oops. The value was 59.5, right? Mean was 49. Standard deviation was 7. That was the right piece, wasn't it? From the right endpoint down. And then subtract off the normal distribution. 45.5, mean 49, standard deviation 7, and cumulative. Square root of 49. I could have typed in square root of 49, I'm just lazy. That's right, I'm inherently lazy. That's the way it works. What's that? What's that? We could have done the same thing like we did in the previous one with the Poisson, or excuse me, with the binomial. There's a Poisson distribution built into Excel, because of course there is. We wanted less than 60, so I have to be careful. I still have to be careful. The Poisson is a discrete distribution. I wanted x is less than 60, so I have to put in what for x here? I have to put 59 in, right? Because it's going to be cumulative up until that point. I still do not want to include 60, right? So that'd be 55, or 59. Try that again. 59. The mean is 49, and it's true. Did everybody see why I put 59 instead of 60? Yeah. So remember the probability said between 45 and 60, but not including the endpoints? I still don't want to include 60 here. It's a discrete distribution, so the next one down is 59. So it's 59 and less. So I don't want to put 60 here.
Because it's not included.
Because it's not included, right. So I used 59. Actually, I could have used 59 and a half here too, because that's just going to ignore the 0.5. Because I can't get 59 and a half in a Poisson distribution. It'll just do 59 and lower. Okay. And then what's that? No, it'll just truncate it. It'll just drop off the decimal. I can try it. Oops. I hate the fact that you try to use the damn arrow key and it doesn't want to work. See? It just ignores it. That's how I would have written the program, so I figured I would have thought of that. The programmers would have thought of that. They're smarter than me. So, back here again. I need to subtract off still the other piece. Where do I want to start the subtraction from?
46.
No, I want to include 46. I don't want to subtract off 46. It's 45. Yeah. Tricky. And again, this reason why I don't want 45, I want the 45 subtracted off, but I do want the 46. I don't want to go all the way to 46. It'll subtract off too much. Notice it's close, but it's not great. It's not the best. Bad math. There are programs when it gives you an error, it'll say bad parse of math. It cracks me up.
I'm a little nervous today, but we're going to see how this goes.
You're a little nervous
I'm
today?
a little nervous. Yesterday was a little much.
Yesterday?
Was it yesterday? Oh, that was good. All right.
Well, he says, I'm going to take mine and try to.
All right. Questions on that at all? You did launch that last.
Well, I was worried about the computer. I'm like, wow, I'm probably back there.
All right. So let's talk about. Are we okay with the approximating the discrete distributions? Does this make sense? The ideas? Yes, Sam.
Are these the only two discrete distributions we're going to be approximating?
Well, you could do this one if you wanted.
Geometric. No way.
No way! All right, how about we do this one?
get it. Get it over with.
It was ugly.
Is the mean for this 1/3?
Yes.
One divided by a fourth is 4, yes. Yeah.
It's still early for me to, I just don't know like the details.
All right, so if we're going to approximate this with a normal distribution, what are we going to use for the mean? I don't think it's 4.
Oh, why not?
Because each individual one has a mean of 4.
What?
Doesn't each individual one have a mean of 4? Yeah? Yeah. That's right. Each individual one would have a mean of 4, right? Because each individual one is being taken from a geometric distribution, right?
But that's still, the P is 3/4, isn't it? And so 1/that is 4.
Oh, it is P 3/4, right. Sorry. So it's 3. Yes?
What?
Wait. No, it's
No, it's the EMF is 1.
P times.
Minus P to the X minus
It's 1
minus
P, right. So
So your 1/P is 1/3/4, right?
yes, so it should be 4/3. Yeah, not 4. That's why that number is too big. Yeah, the 144 seemed huge.
4/3 times 30.
Yeah, this number is your P, not the 1/4. Ah, that's much better. Yep. So the mean here for each individual one is 1/3/4. It's the 1 over the P. So then the mean of the sum will be the 36 times the 4/3. And 144 was going to be way too big for the distribution. That was where the 48 comes from. What about the variance for each? Okay.
0.444444.
Or that. I may be happy. So what will be the variance then for the whole thing? It's 1 minus P over P squared. 1 minus P over P squared. What's it going to be?
That times 36.
Yeah? It's good to me. Oops. All right, so what probability should we compute if we're trying to approximate? Jeez, this one. Say that again. Yeah, feels good. Probably a while. What does y have to be in between? Good. And again, we want it in between, right? We want to make sure we want to use the halfway in between two integer values and catch the boundaries, right? So we need to be above the upper bound and below the lower bound because both of them need to be included. Does that make sense? So then this will be phi of the 49.5 minus 48 over 4 minus phi of 45.5 minus 48 over 4.
That's right.
Yeah? Are we happy?
That's phi of 3/8 minus 1 plus phi of 5/8.
Or we can go do it in Excel. Are we happy with this setup though?
I'm different for you.
Thanks, Mike. Yeah, Sam.
So I was confused when we were setting up the problem. How come it's not negative binomial? Is it because it's all from the same distribution?
Oh, you could do the negative binomial. That's fine, because that's how you would compute it, right? So the sum of the geometric would give it that way. You can think of it that way. It's all right. What would be different? What would be different about part B? Oh, it was right there. Yeah. What would be different about part B?
This one's not something.
Well, it is.
It's the mean, it's just
Okay. So what are the mean of the variance going to be? Which is? That was the mean of, there you go. All right, the mean of the x bar is the mean of the individual ones, right? And then what's the variance?
that divided by n.
What divided by n? What was the variance? There you go. Because remember, it's sigma squared over n, and I was at the bottom of the screen. So I just write it as a multiply by the reciprocal idea. And then you would do the exact same thing, right? Just using this mean and that variance. Right? Because we're divided by the 36 because there's 36 in the sample. Yeah. Yep. That was our central limit theorem idea, right? We okay with that? All right. Well, let's talk about some of the new stuff, even though I only got about 8 minutes, maybe. All right. 7 minutes, maybe. All right. So the video I asked you to watch was about what we refer to as maximum likelihood estimators. And the idea, again, behind it is to try to come up with a method based on whatever sample that you have that gives you your best possible estimate for a parameter. So my example in the video was you assume that you've got something that is distributed with a Poisson distribution, and you're trying to estimate from a sample of whatever that sample happens to be, you're trying to estimate what your best guess is for what the lambda needs to be, because that's the parameter for the Poisson, right? You're trying to figure out what's the best guess for what the lambda is based on the sample that you have, right? So the whole point of that was just to introduce you to how you compute this, what we refer to as maximum likelihood estimator, right? So the likelihood is just the product that you actually got these things out of your random sample. In a discrete perspective, that's actually just plug it into the PMF and multiply it together, right? You know what the PMF has to look like. You would plug each individual thing in and multiply them, right? Now for continuous distributions, that's obviously not how you would compute likelihood, right? Because the likelihood of getting an individual piece is 0, right? However, we still define likelihood in that same way, right? We're trying to take our PDF and maximize it according to this sample, right? Plug it in, multiply it together, and maximize it. And we use calculus techniques, at least for part of it. We're going to have another way to do it too. Pardon me. But we use calculus techniques, but of course we have this product that we're trying to differentiate, so we use a logarithm to help us change the product into a sum, right? So let's see, even though I wrote that as notes, let's see if I have an example here real quick. All right, so not too worried about the setup of the action, what this is called a Weibull distribution, but it's this PDF that I'm interested in here. This 2 over beta squared x e to the minus x over beta quantity squared. What I try to use, it asks you to use that sample to calculate an estimate for beta. So again, the idea here would be you're taking this sample, you think you've got a PDF that describes your distribution based on past experience, most likely, or other people's experiences with these types of data. You're trying to figure out a way to estimate the PDF for your purposes based on your data. So we want to use the one that maximizes the likelihood. All right, so shoot. We calculate our likelihood function. So our likelihood function of beta, based on the sample, is a product, and I'm going to just do this generally, and then we'll worry about the individual sample pieces later. It's a product of your PDF based on the parameter. That's how we define our likelihood function. It's a beta. All right, so for our purposes then, we get 2 over beta squared x e to the minus x over beta squared. X sub I, sorry. These are all i's. So this is an x sub I, and this is an x sub I. Now again, we're trying to maximize this likelihood function in terms of beta. That would be a crappy thing to try to take a derivative of, right? It would be a nasty product rule to do. So that's why we do the log, is to change that into a sum, right? Okay, so when we hit the product with a log, it changes it into a sum, and it changes this into a sum, right? So we get what? Well, I hit this way, it changes this whole thing into a sum. This will be a difference, so this will be log of 2 minus 2 log of beta, right? Plus log of x sub I. And then log and e will cancel each other out, so then we'll just get minus x sub I over beta squared. I can't do that because there's not a log there anymore because the log canceled the. So there's no log there. But otherwise, yes, you would have been able to bring it down. Everybody see where I got this? I did that quickly, but I got about 2 minutes. So I was trying to hurry. Yeah? Okay. Now, we want to maximize this thing, so we want to take its derivative. Nice thing is that we're differentiating this with respect to what? Beta. So it doesn't have a beta in it. What's the derivative going to be? 0. So that's going to go away, and that's going to go away, right? All right, so we take the derivative. We get -2 over beta, and then this part becomes, that's just x of I squared over beta squared. So we're going to get what? Plus 2x of I squared over beta cubed. Can we differentiate that? Because it's x of I squared beta to the -2. What minus sign? This one? Well, it's beta to the -2, so it becomes positive when I differentiate. Right? I mean, it's certainly possible I screwed that up. But in this case, I think I'm okay, right? Beta to the -2, so it's -2 beta to the -3, so it makes it a positive. Right? We're maximizing, so what do I want to do with this log, this likelihood function? Your critical values, right? Set it equal to 0 and solve for beta, right? So that's what we would do next, right? Set it equal to 0 and solve for beta, which I'll do next time because I know people have to run to school. I'm really trying to be cognizant of when you have to run to Scoville in 10 minutes.
I'm proud of you.
I'm doing my best.